Let's talk about a new kind of computer, one that's being built right now, but doesn't play by the rules of the world we see every day. Today, we're diving into quantum computing, a technology that uses the, frankly bizarre laws of quantum physics to solve problems that are literally impossible for even the fastest supercomputers on Earth.
You know, everything in the computers we use today, your phone, your laptop, it all boils down to the bit. It's just a simple switch, right? It's either on or off, a 0 or a 1. But the power of quantum computing comes from something totally different, the qubit. And the best way to think about it is like a spinning coin. While it's spinning in the air, it's not heads and it's not tails. It's kind of both at the same time. That's the qubit. It can be a 0, a 1, or a mix of both, all at once.
So, this wild ability for a qubit to be in multiple states at once gives it some incredible capabilities. You could seriously call them superpowers. So let's break down the 3 fundamental quantum rules that make this all happen.
Okay, superpower number 1 is called superposition. And this is exactly that spinning coin idea we just talked about. A qubit holds the potential of being both 0 and 1 at the same time. It's only when you measure it, when the coin finally lands on the table, that it collapses into a definite state, either heads or tails. This ability to hold all these values at once is what lets the computer explore tons of different possibilities all at the same time.
And here is where you really start to see the power of that idea. Look, 3 normal bits can only store one number at a time, like 101. That's it. But 3 qubits in superposition, they can represent all 8 possible combinations at the exact same time. This is how a quantum computer can search through a huge number of solutions all at once.
Now, the second superpower is even weirder, if you can believe it. It's called entanglement. This is this deep, almost spooky connection between 2 or more qubits. If you have 2 entangled qubits and you measure one and find out it's a 0, you instantly know its partner is a 1, even if it's on the other side of the planet. They're linked. They act like a single, incredibly powerful system.
And this is where the power just becomes exponential. It's not just about adding qubits, you're multiplying their potential. Just 20 of these entangled qubits can represent over 1 million classical values at the same time. Get a few hundred of them together, and they could represent more states than there are atoms in the entire known universe. It's just mind-blowing.
Okay, so if you have all these millions of possibilities floating around at once, how in the world do you find the one right answer? Well, that's where the third rule, interference, comes into play. Quantum algorithms are designed to cleverly manipulate the qubits so that the paths leading to the wrong answers basically cancel each other out, like waves in a pond. And at the same time, the paths leading to the right answer get amplified. You're sort of nudging probability. So when you finally measure everything, the correct solution is the one that's most likely to pop out.
So, we have these amazing, mind-bending theories, but how do you actually build a machine that can do all this? Well, it turns out that trying to harness these quantum superpowers requires some of the most extreme and demanding engineering on the entire planet.
For starters, most quantum computers need to be kept ridiculously, unfathomably cold. We are talking about minus 273 degrees Celsius. That's near absolute zero. To put that in perspective, that is colder than the empty vacuum of deep space. And why? Because any heat at all is basically noise. It's vibrations that can easily mess up those super delicate quantum states and just completely wreck the calculation.
And getting things that cold is, you can imagine, not easy. It means taking the quantum chip, putting it inside a vacuum, and then hooking it up to these enormous multi-stage machines called dilution refrigerators. These things are incredibly complex, and they use a rare mix of helium isotopes to suck every last bit of heat out of the system. It's a hugely expensive and energy-intensive process.
And the cold? That's just one piece of the puzzle. Scientists are also fighting this constant battle against something called decoherence. The best way to think of it is the quantum state just fading away or popping like a soap bubble the second it interacts with the outside world. A tiny vibration, a stray magnetic field, poof. It can happen in microseconds. On top of that, you've got high error rates, the huge challenge of scaling from hundreds to millions of quantums, and the need to invent whole new ways of correcting for all those errors. So with all of these absolutely incredible challenges, you really have to ask yourself, why are we even bothering? Why go through all this trouble? Well, the answer is that if we can crack these problems, the payoff could be nothing short of revolutionary. Let's take a look at the kind of world-changing problems these machines are being built for.
So, just to be clear, these things aren't going to replace your laptop. They're specialized machines for ridiculously hard problems. Think about medicine. They could simulate complex molecules to design brand new drugs in, like, months instead of decades. Or in finance, they could tackle the mind-boggling complexity of global supply chains. And here's a big one. In security, they could theoretically crack the encryption that protects almost all of our data today, which means we'd have to build a whole new quantum-safe internet. The list just goes on and on.
So where are we today with all this? Well, we're in this really fascinating moment, this transition period. We're moving from the early experiments to machines that are right on the edge of being truly useful.
You know, the idea was first picked around by the physicist Richard Feynman back in the 80s, and it got a huge boost in the 90s with some breakthrough algorithms. But things got really serious in 2019. That's when Google claimed quantum supremacy. Now, that doesn't mean their computer was better at everything. What it meant was their Sycamore chip did one very specific, very complex calculation way faster than the world's best supercomputer ever could. And ever since then, the race has been on. Right now, we are living in what people in the field call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, it means our machines have a decent number of qubits, dozens, maybe hundreds. And they're powerful enough to do some cool stuff. But they're still too noisy, too prone to errors, to be the perfect, reliable calculators we eventually want.
So the ultimate goal, the thing everyone is racing toward, though it's probably still 10 or 20 years away, is something called fault tolerance. The idea is actually pretty clever. You use thousands of these noisy, error-prone physical qubits, and you get them to work together to create a single, stable, and nearly perfect logical qubit. It's kind of like having a whole team of people constantly checking each other's work to make sure no mistakes slip through. That's how we'll build a machine that's truly reliable for the big stuff.
And that really brings us to the final and I think most profound question. Richard Feynman once said that nature isn't classical, so if you want to make a simulation of nature, you'd better make it quantum mechanical. So, if we pull this off, if we actually build a machine that can perfectly simulate the building blocks of our universe, what's the first great challenge you would ask it to solve?